students, today we're going to learn how to logically test sentences using truth tables. Some of the practical goals, we're going to learn how to be able to test to see if someone is contradicting themselves, to test to see whether people are lying, and to test to see what the logical implication of claims are. So if statements are consistent, what does that imply about the state of the world? So again, we're using these definitions of our connectives that we represent in these matrix. In propositional logic, these represent the truth values for each of the defined connectives. So negation operates to turn the true to the false and the false to the true. And is true when both conjuncts are true, otherwise it's false. Or is false when both disjuncts are false, otherwise it's true. If then is false when the antecedent is true while the consequent is false, otherwise it's true. And finally, if and only if is true when both parts agree. So true if and only if true is true, and false if and only if false is true, otherwise it's false. So if you have not memorized these, you might want to print this out so you can use them while you are filling in your truth tables. So take out a pen and paper. I'm going to teach you how to create truth tables in order to classify a statement by itself. So you're going to write the proposition out across the top of the matrix, and that's going to determine how many rows you have under the proposition. So if you only have one proposition in the claim, then you only have 2 rows, 1 row for true, 1 row for false. If you have 2 propositions, then you have 4 rows because you have to do all the propositional possibilities. So both true, both false, the first true while the second false, the first false while the second true. Those are 4 different possibilities. And finally, if you have 3 sentences, you're going to need 8 rows. The way to determine this is 2 to the nth power, n being the number of propositions. That determines how big the matrix is. You're going to divide horizontally underneath the proposition to create these rows. It's going to look like this right here. You're going to classify the statements according to their value in relation to themselves. In order to do this, you need to calculate the number of different instances of letters and connectives to figure out how many columns. So here we have 1 tilde, then we have P, and we have P repeated, and the and. You'll notice that the parentheses do not get their own column because they're not doing any logical work. They're not functioning on the parts. Also, the slash that's going to separate sentences when we evaluate sets of sentences does not get their own column either. But you need to leave them in to make it clear what the grouping or what the separations are. So what we're going to do next is we're going to fill in the values for the variable first, okay? I'm going to go on. I'm going to do this in 1 second, but first I'm going to read the rest of the rules. You're going to fill the truth values of variables first to represent all possible truth values, remembering always that if you assign a value of T to a P on a certain row, wherever P pops up, you need to keep that T because P equals P. Also, you're going to do the Russian doll principle. Always do the minor or the inmost operators first and then work outwards, doing the major operator last. Okay, so here we're going to do these together. So here we go. We're going to fill in the possible truth values first for the variables. So either it's true or P is false. Those are possible truth values. Okay. Then we do the inmost first. So true and true is true. And false is false. Then we do the major operator last. The major operator is the one outside the parentheses here. And this negation is operating on this row right here. So it turns the true to false, and it turns the false to true. So if we were asking what type of sentence this is, we would say this is contingent, meaning it's sometimes true and sometimes false. So here we're going to do this two variable one together. So again, we're going to start with filling in the possible values. So here I like to start by going top half true, bottom half false, and then dividing in half. So Q will go true, false, true, false. Okay. Then we have to do the minor operator first. So the negation is going to work on this Q directly. So we go false, true, false, true. Now we're going to do the major operator, this OR. Okay, and if you don't remember the rules for OR, I have them over here above the pedestal. So true or false is true. True or true is true. False or false is false. And false or true is true. So the answer for this one is also contingent. Sometimes it's true and sometimes it's false. Our last big one we're going to do is we're going to do this 8-row one because we have P, Q, and R, and those are all different ones. I'm going to turn the color, different color. So here we go. So P, we're going to start with P. We're going to do all true on top. So that's going to be 4 trues in a row. Then all false on bottom. We should have equal numbers of trues and falses. Then we're going to do Q next, and we're going to divide it in half. So it goes true, true, false, false, true, true, false, false. And the last one is R. We're just going to divide that in half, and that ends up being true, false, all the way down. True, false, true, false, true, false. Now, if I have a big one like this to double check, I can see that all true are on the top and all false are on the bottom. And that helps me double check and make sure that I've done the correct amount. Next, I'm going to fill in the negated R. So we're just going to do our false true pattern all the way down. There we go. So now we're going to do our minor operator, our OR, and this is operating between this, the Q, and this, the negated R. So this column here with the negation. So true or false is true. True or true is true. False or false is false. False or true, still true. True or true, true. Sorry, true or false, true. True or true, true. False or false, false. And false or true, true. So now we're using this column right here to compare with the P column here to get our final column here with our if and only if. So true if and only if true is true. True if and only if true is true. True if and only if false is false. True if and only if true is true. False if and only if true is false. Remember, they have to equal. False if and only if true is false. False if and only if false is true. And false if and only if true is false. So there's our answer for our major operator, our if and only if. So when we logically classify statements, what we do here is we look to see under the main operator. So here we're going to do P implies P. So either they're both true or they're both false. So true if and only if true is true. False if and only if false is true as well. So if P implies P is a tautology. Okay. Next, we'll do this one here with our Q and not Q. Again, we're going to have our values be the same because Q equals Q. And the negation of Q, we're going to put that in before we do our main operator. So this is our and. True and false is false. And false and true is false as well. So this one is a self-contradiction. The last possibility is contingent. This can be possibly true, possibly false. So far, those are the ones that we have been looking at. Chances are any statement will be contingent. So we're going to fill these all in. So here we go. True implies false is false, and false implies true is true. So this one is sometimes true, sometimes false. So that's how you categorize the different statements in relation to themselves. So now I want you to work on these problems here. On the next one, R and R, Q and S, if and only if not Q and not S, and not P implies Q implies P. Okay. So set those up, and then I'm going to go back and I'm going to ask you questions to make sure you know how to set these up. So first, how many rows are there for the matrix for R and R? For this one, you're again going to figure out how many different types of propositions, okay? And then you're going to figure out how many rows that is. How many rows in the matrix for Q and S, if and only if, parentheses, not Q and not S, end parentheses? How many columns in the matrix for R and R? And how many columns in the matrix for Q and S, if and only if not Q and not S? Okay. Okay, here we go. So first we're going to do R and R together. So we have true and true, which is true, and false, which is false. So this sentence is sometimes true and sometimes false. We call that a contingent sentence. Contingent. It's hard to write it out. Okay, here we go. Now for this one, I've already filled in the negated version of negation Q and negation S. This is going to make it easier for us to fill these in. So the and is true when both parts are true, otherwise false. And for this column here, false and false is false, false and true is false, true and false is false, but true and true is true. Now we have an if and only if that we're going to use for these two, for our true and false on this first line. So that's true if and only if false is false. But false if and only if, false if and only if false is true. False if and only if false is again true. And then false if and only if true is false. Because again, they have to match each other. Okay, I'm going to clear this one. Oh, for this one, again, this is contingent. Same answer. Now here's our negated P implies Q implies P. So we have to start on our innermost. Again, we've already put our negated simple sentence in. And here we go. True, then true is true. False, then true is true. True, then false is false. and false, then false is true. So now we're going to use this column here with the negation. So false implies true is true. False implies true is true. True implies false is false. And true implies true is true. So here is our value. And again, it's contingent. Now you're going to learn how to solve a word problem on a single statement. And what you're going to do is you're going to symbolize the statement as a well-formed formula, and then you're going to construct a truth table to see if the main operator has all true, meaning tautological, all false, meaning self-contradictory, or at least one false and at least one true for every space in the main operator's column. You're then going to figure out what the question is asking for. For example, if it's asking if it's lying or nonsense, is it contradicting itself? So here we go. I want you to create a truth table for the statement below. Is Kevin talking nonsensically? So I'm going to have you pause, write this down. So create this in your well-formed formula. Okay. And then you're going to write out the whole truth table. And then you're going to answer if this is self-contradictory, meaning is he talking nonsense? So here we go. I'm going to do this with you. Okay, so I've already filled in the negated simple propositions, but the ones that are negated that aren't simple, I haven't filled in yet. So we're going to start with our and on our innermost here. And for this one, I'm just going to fill out, here we go. So true and false is false. True and true is true. False and false is false. And false and true is still false. So we've got lots of falses here. And then we've got our and here. Okay, so we got false and false is false. False and true is false. True and false is false. True and true is true. False and false and false and false. Sorry, false and true and false and false. And false and true is all false. Okay, now we're going to do our inmost here, P and A. So we get true on the top, and then the rest all the way down are going to be false. Now we negate these, so we turn the true into false, and we turn the false into true. So that's a lot of trues there. Here we go. Because it's operating on this column right here. Now we're going to use this column with this column. So remember, whenever it's false, the whole conditional is true. And the only time it's false is right here when you've got a true antecedent and a false consequent. So there and there. And that's true and that's false. There we go. So now we're going to work on this in between. So this is an and. So we're going to go from this right here column here and this column here. So true and false is false. False and true is false. True and false is false. False and false is false. True and false is false. False and false is false. So here we have the answer. Yes, he is speaking nonsense because in the main operator, it's false. So this is a self-contradiction. Did you get the right answer? Now we're going to talk about creating truth tables for classifying sets of statements. So not just one statement, but more than one statement. So you're going to set it up the same way that you would set up it if you're just classifying a single statement, except you're going to put one slash between each of the statements. Again, remember the law of identity. Make sure that the value for each simple proposition or variable stays constant throughout the truth table. I mean, if you assign P on a row in column 3, when P again appears on that row, it has to be true as well. You're going to classify sets of statements as either logically equivalent, contradictory, consistent, or inconsistent, according to the possible truth values indicated. I want you to do it in this order to test, first to see if it's logically equivalent, then contradictory, then consistent. If it's not any of those, it will be inconsistent. This gives us our most precise answer. So check first to see if it's logically equivalent. Every value under the main operator is the same for each statement. So when one is true, the other is true, and vice versa. If it's not logically equivalent, and again, you have to do this all the way down the column to the very bottom row. If it's not logically equivalent, check to see if it's contradictory. When one is true, is the other false, and vice versa, all the way down. If not, see if it's consistent. This means that on at least one line of the truth table, one row, you have them both true. So can they both be true at the very same time? And finally, if it's not consistent, it'll be inconsistent. It's not logically possible for them to be all true at the same time. So here we go. Let's practice. First, we're going to do a logically equivalent set of statements. So we fill in our value, our simplest ones first. So we got false, false, true, true. False, 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 true, false, true. So we got our and. Our and is only going to be true on the very last line. Otherwise, it's going to be false. Now we're going to do our negation of P or Q. This is our neither nor. Now we're going to go inside here. So this is going to be true, 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 false. And then we do the negation of it. So the negation of true is false. Negation of true is false. And finally, last line, negation of false is true. So now I want you to compare this column here with the main operator here. So first we go line 1, both are false. Line 2, both are false. Line 3, both are false. And line 4, both are true. So these are what we call logically equivalent statements. Or as we put it in informal language, these mean the same thing logically. Next, we can have contradictory statements. So for these, I'm going to start with my and because this one's the easiest. It's going to be true on the top, otherwise false. Now I'm going to do my P, then not Q. So here we're going to go true then false is false. True then true is true. False then false is true. And false then true is true. So now we're going to go line by line. First, we're going to check to see if it is logically equivalent. So on the first line, one is false, while the other is true. So now we know they're not equivalents. Now we check contradictory. So they contradict each other on the first line. One is false, the other is true. On the second line, one is true, the other is false. One is true, the other is false. One is true, the other is false. So it contradicts itself all the way down. So these sentences are contradictory. Next is consistent statements. For these, they just are not logically, we've already eliminated logical equivalence and contradictory, and we are looking to see if they can be true at the same time. So here our if then for P then Q goes true, false, true, true. And our Q then P goes true, true, false, true. Now, they are logically equivalent in line 1, but they are not on line 2. And because they're equivalent in line 1, they're not contradictory. Thus, we can check for consistency. Can they be true at the very same time? And we find that on line 1. As soon as we find it, we can stop looking because these are consistent. Last are inconsistent statements. These are ones that are not contradictory, not logically equivalent, and not consistent. So here I'm going to start with my and again because it is the simplest to fill in. Out of the two we are comparing. So we've got true, false, false, false. Then our if and only if goes true. True if and only if true is true. True if and only if false is false. False if and only if true is false, and false if and only if false is true. Then we negate this if and only if, and we get false, true, true, false, because we're operating on this row right here. And now we're going to first test logical equivalent. Nope. And it looks contradictory at first. So they're contradicting themselves on line 1, on line 2, on line 3, but they do not contradict themselves on line 4. Those are not opposite values of the same value. And then we look to see if they can both be true. And because they're only true on line 1 for P and Q, we check for line 1 and they're not both true. So they're not consistent, therefore they are inconsistent. So here's an exercise for you to do. You ask your significant other where he was, and he says, it's not that me being at the pool party implies that I was swimming, but his roommate had said earlier, either your significant other was swimming or he was not at the pool party. Create a truth table to test, can they both be telling the truth at the same time? Why? Logically. Sorry, I by accident moved ahead. So again, here is the original one. Here, pause it and please write down your answer and then do your truth table. Can they be telling the truth at the same time? In other words, can they be consistent? Why? Logically. Okay, now we're going to do this exercise together. So here we go. We're going to start with our or over here. So true or false is true. False or false is false. True or true is true. And false or true is true. Now we're going to do our if then on the inside. So we get true, false, true, true. And now we do the negation on the column here. So we get false, true, false, false. Okay. Now I want you to test and see if they are consistent. Can they both be telling the truth at the very same time? So line 1, they aren't both true. Line 2, they aren't both true. Line 3, they aren't both true. Line 4, they aren't both true. So they are being inconsistent. So somebody is probably lying. Now I want you to continue practicing. Do this exercise on your own. Okay. Once you've done that, pause this, do that, and then we're going to do this together. So for the if then here, it's going to be false when the consequent is false and the antecedent is true, otherwise true. And this one is false when either conjunct is false, otherwise true. So here we go. Now let's test. Are they logically equivalent? Nope. Are they contradicting? Well, yes, yes, nope. So right here we have them as consistent. Here's a longer one for you guys to do. Pause it, test yourself. Are these logically equivalent, contradictory, consistent, or inconsistent? And here we go on this one. This is going to take us a little bit, so I'm going to pause it and fill it in one block at a time. So I filled these in for our ors, and now I'm going to fill in the ands. So here we have the negated A, so we have to use the column that's negated. So this one's going to be false, false, true, false, 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 true, true. Okay, then we're going to go over here to this one. We have true and true is true. True and true is true. True and false is false. True and true is true. Then we have false and true is false, false. The rest all the way down, we got to do false. Okay. Now we're going to test to see, compare these two. So we're using this column here with this column here. So they are not logically equivalent. Now we're going to see if they're contradictory. So here we got contradicting, 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 contradicting. Oh, not contradicting. They're both false there. Now we're going to test to see if they're consistent. So is there any line on the truth table where they're both true? And the answer is no. So the answer for this one is inconsistent. Last ones are going to be some informal language exercise. Esther says, if you don't love me, then I'm certainly not going to have sex with you. Otto responds, that means if I do love you, you will have sex with me. Is Otto being rational? Meaning, are these two statements logically equivalent? If not, under what conditions do they differ? In other words, when do these sentences logically differ in value, and what does that imply about what the two think? So here we go. This is the way to translate these. If I don't love you, then not sex. And then Otto says, well, that means if you do love me, then sex. Okay, so we're going to fill this out and see if Otto is correct. So false implies false is true. False implies true is true. True implies false is false. And true implies true is true. Now we're going to do L implies S. So true implies true is true. True implies false is false. And false implies true is true, as is false implies false. So now we're going to compare. They do agree on the first line, and they agree on the last line, but they differ on these two lines. Okay? So she would be lying in case here in which she doesn't love him, but she does have sex with him. Whereas he is implying she would lie if he does love her and she doesn't have sex with him. But I want to be clear. The difference really is that she's only talking about conditions when he doesn't love her, and he's only talking about conditions when he does. So that's where they differ, and no, they're not logically equivalent. And here's the last one. You are undercover at a bowling alley. You overhear three pals hypothesizing about an art heist. Suppose they are all making true claims at the same time. What information can we learn from what they say? Okay, so D starts, she says, I did not go into the museum, and if Mac was involved, so was Charlie. Charlie says, look, if Mac was involved, then D went into that museum. And Charlie says, well, Mac says, if Charlie was involved, then I was too. So before you go on to the next part, make sure you put these into your symbolic form. write them horizontally across, and now you have 3 separate propositions. So make sure that you have 8 rows underneath for your matrix. Okay, now we can reveal how to do this. So again, we filled in the easiest ones to fill in. And I'm going to pause this so that I can fill a bunch. Okay, here's the completed matrix. Check your matrix against this. And now let's figure out what we figured out. So I left the main operators in blue, and we're going to compare the blue columns. So we're just trying to see if they can be consistent, okay? So on line 1 through 4, the first sentence is false, so they can't be consistent on one line, lines 1 through 4. Line 5, we got true, false, true, so not consistent. Line 6, we've got false, false, true, so not consistent. Line 7, we got true, true, false, so not consistent. But on line 8, we have true, true, and true. So if they are being consistent, what do we learn about them? Well, we learned that each of the values of these sentences would be false. So D did not go into the museum, Mac was not involved, and neither was Charlie. That is what we would learn. If they're being consistent, then all of those propositions are false. So you learned how to use truth tables to determine whether an informal or symbolized sentence is contingent, tautological, or self-contradictory, and also how to use truth tables to determine whether sets of sentences are logically equivalent, contradictory, consistent, or inconsistent.